All right. Okay. So we are recording now. All right. So here, if you get a negative value, once you calculate the excess kurtosis, it means you're looking at a platykurtic distribution. Okay? Now, generally, it's discussed in terms of how peak the distributions are. And for our reference, because we're studying financial econometrics, we are more interested in the tails of the distribution. Okay? So generally, they have higher peaks and thicker tails. Okay? Whereas this will have a thinner tail and a lower peak, the platykurtic distribution. So yesterday we were discussing how for a risk-averse investor, okay, you will find that if he finds that the distribution of the asset that he is interested in, okay, that is following a leptokurtic distribution, then he'll probably not want to invest in that asset. Okay, since he has a higher probability of getting extreme returns, whether it's positive or negative. But since there's a higher chance or likelihood that he will get extreme returns or values, so he'll prefer not to invest in that particular asset. Okay? So probably it will be safer to invest in an asset which has a platykurtic distribution. Okay? So this is something that we were discussing yesterday. Do you all still have doubts about this?
Ma'am, I have a doubt.
Yeah.
So,
Go
ma'am,
ahead.
what do these tell us about the outliers in our data set? Skewness and kurtosis. How can we use them to determine some outliers, something about outliers?
Okay. Okay, so leptokurtic distribution will tell you that you have higher outliers, okay, a large number of outliers which are in the tails. That's why they have those thicker tails, okay, whereas this area over here, okay, which is around the mean is much lesser. Okay? If you look at the area itself, so here you will find that since the outliers are larger, okay, they'll tell you what is the kind of risk involved in different assets. For an asset, if you find that the return distribution is leptokurtic, just like I mentioned, you'll find that it's susceptible to extreme returns, okay, either extremely high returns or extremely high negative returns. Okay? So in this case, you'll probably want to invest more carefully. If you're a risk averse investor, you will not want to invest in such an asset. Okay? Similarly, if you look at the platykurtic distribution, the possibility of getting outliers is far less, okay, in such a distribution. So they are considered relatively safe. You have an asset return distribution which follows the platykurtic distribution. Normal distribution, of course, we generally assume that returns follow a normal distribution whenever we are carrying out our exercises. But later, when we are modeling risk, we'll probably look at how we can use leptokurtic distributions and so on. That will come a little later in the course. Okay. So probably once we go into modeling volatility and all those things, you'll understand this portion a little better. But it's important to keep in mind that these moments, the first 4 moments, basically tell you that they help you describe your distribution a lot better compared to just looking at the first and second moment. Okay? Because you
Ma'am,
can
doesn't the
understand.
platykurtic distribution has more risk because it is more spread out, as we can see?
Yes, ma'am.
Yeah. So
Yes,
if you
ma'am.
look, yeah, when you look at this image, it will look like that, okay? But actually, since in this graph, both end at this point and they're probably stretching all the way till here, okay? But if you look at other diagrams, you'll find that this tail area is generally bigger for the leptokurtic distribution, okay? So you'll find that there are larger number of outliers in such distributions. Just pick up any statistics textbook and just go through these diagrams and what it says about each of these distributions. Okay, generally you'll find that a leptokurtic distribution has a higher chance or has a larger number of outliers, whether it's positive values or negative values. So you get more extreme values here, which will lie in the tail, whereas this will be far shorter or smaller. Okay? Even if you look at the shape of the distribution itself, you can see here the returns that you'll probably consider safer, which are closer to the mean itself. This whole area is a lot less, right? It's more squeezed compared to this area, okay, for the platykurtic distribution. So you can imagine that there's a greater likelihood that you'll get more returns in these regions, extreme regions, if you have a leptokurtic distribution compared to a platykurtic distribution. Okay? Uh, this diagram itself might not give you an idea of that, okay, because of the way this region looks. Just pick up any other statistics textbook. It will be better if you look at a textbook, okay, and then look at these components over there. So you'll find that what I'm discussing or saying right now is true, that you get larger extreme values for a leptokurtic distribution and not for a platykurtic distribution. And somebody was mentioning yesterday that the T distribution is has a lower peak or a smaller peak compared to the normal distribution, but it's still considered a leptokurtic distribution. Okay, so that is right. Okay? That's something that even I mentioned, but the person was right who said that the peak is lower. Okay, so that you can probably consider that as an exception, and generally that's the case for a T distribution with smaller degrees of freedom. Okay, you'll find that that is true, that the peak is lower and the tails are thicker. Okay, so that is one exception. I would just encourage you all, since you're not getting a clearer picture from this image itself, to take a look at any basic statistics textbook. Okay?
Ma'am, I have another doubt.
Yeah.
Yeah, so when our distribution is positively skewed, does that mean that we have outliers towards the positive side?
Yeah, you'll have more values here, okay, in the right tail, since that
Okay,
tail is
so
longer.
in case of returns, a positively skewed distribution would be preferred.
Yes, I think you can say that. Okay.
Okay, thank you.
We'll see if we can do some of this in the modeling part. Okay, once we start doing the practicals, we'll actually get, once we load the data, you'll be able to get the summary statistics or descriptive statistics of the data. Okay, so it's usually automatically calculated. So over there, we'll be able to look at the actual values that we are getting, so that we can understand what sort of distribution that we are looking at in terms of returns. Okay, so this is something we'll do probably next week. We'll do a little bit of practical, so we'll do that at that point of time. Okay, so for this right now, just keep this in mind. If you're still not convinced, just take up any textbook and look at the distribution, see what they mean. Okay, then probably it will be a little clearer to you all. So we'll just come back to
Ma'am, Neil has, I guess, raised his hand, so he must have some question.
Oh, no, that's done. That's done.
okay, you asked that question, is it?
The same point of contention which was being raised by the others regarding the ends and yeah.
Okay, okay. There are other images, just take a look at that. Okay, you'll find loads of images online. So each one will look a little different basically, but if you look at the information that is given about each of those distributions, then you'll see that what I was saying is right. Okay. All right, so yesterday we stopped at the point where we were discussing stationarity, right? Okay. And we discussed what is meant by strict stationarity and weak stationarity. For any of our empirical work, for all the practical work that we'll be doing, we are focusing on weak stationarity. All right. So any time series is said to be weakly stationary if you find that the mean of that time series is constant, okay? The variance is constant and finite, and the covariance between xt and its lags. Okay, if you have a process xt, the covariance between xt and its own lagged values or past values depends only on the lag or the difference in time. Okay, so this gives you the difference in time, s minus t. So it will depend only on the lag and not on the actual moment in time that you have used to calculate the covariance. Okay. Now, generally, because I had mentioned this, because if you're taking for covariance, if you're taking a situation where T is equal to S, okay? So the covariance formula will simply reduce to variance. So generally we say that if a time series is mean and covariance stationary, then it is said to be weakly stationary. Okay? So we'll just try and take a look at it. Yesterday I was trying to describe it. Okay? So today we'll actually try and look at it with some data. Okay? So just a visual inspection. Later when we're doing the practicals, we'll actually do tests of stationarity and we'll try and see if a time series is stationary or not using tests for stationarity itself. So you all can see this Excel sheet, right? Can you all see this?
Yes, ma'am.
Yeah, okay. Uh, so here I've taken the closing prices for Infosys. Okay, this is daily data. I've started from 2020. Okay. This is August 2020 to here August 2021. Okay, 24th August 2021. So I've taken daily data. And these are the closing prices that I've used for Infosys. Okay. Now, based on these prices, I've just calculated the simple returns, and these are your continuously compounded returns or the log returns. Okay. So now we'll just try and take a look at whether these are stationary or not. Okay. This is just a visual inspection, so we might not be accurate. Okay. We might not be 100% right, but it'll just give you a basic idea of what we mean by stationarity. Okay, so right now I'm just plotting the prices itself. Okay, you can see that there's some sort of an upward trend in the prices, right? You can see that it's sloping upward gradually. So now, because of that trend, that slight positive trend that is there, you can probably conclude that the mean is not constant. Okay, that the mean of this series is not constant. Probably if I take two windows, okay, if I take this point, for example, and if I take this point of data, if I take the same sized windows or subsamples of this data, I'll probably find that the mean in these two subsamples is not the same. Okay? So here you can say that it's violating the mean stationarity condition. The mean is not constant over time. Okay? This is clear to everyone? You all
Yes,
are
ma'am.
able to see this, right?
Yeah.
Okay, fine. Whereas if you look at the variance, okay, there isn't much fluctuation as such. Okay, so we can't really draw a conclusion about the variance. It might be variance stationary, it might not be. Okay, so once we actually conduct tests, we'll be able to conclude about the variance. Okay, but as of now, you can already see that it's violating the mean stationarity condition. So we can conclude that the series is not stationary. Okay, weakly stationary. Okay, now if you look at this is a plot of the log returns. Okay. So now if you take the log returns itself, you'll see that they are fluctuating about some constant value of probably 0. Okay. So you can see that the fluctuation is quite constant. So you can be somewhat confident, reasonably confident that the mean is constant for all time, okay, for this entire data set that we have. What do you all think about the variance?
Ma'am, variance is constant, but in later part, like after 25 to 25 in the month of from April to which month? July, the variance has scattered. Like it is not constant in this 2 or 3 months, ma'am.
Okay. All right. So that is something that one of you has noticed. Okay, so you feel that around this portion, the variance might be different compared to the rest of the data set. That's what you're saying, right?
Yes, ma'am.
Okay. So again, visually just looking at it, we can't be sure because the size of the spikes here, okay, it's slightly different in some regions. So again, we might not be able to draw a conclusion about variance stationarity here, okay. But in terms of mean stationarity, it's probably looking like it's mean stationary again, okay. And if you probably ignore this portion, but maybe for this portion you might feel that since the fluctuations are more or less around the same size except for these, okay, you might think that it is variance stationary. Okay, but again, we can't draw a conclusion just by looking at it. Okay, so this just gives you a vague idea, okay, about what you need to do or how you might need to transform your data and so on. Okay, another factor is that since I've taken the daily data and then I haven't seasonally adjusted it. Okay, so you might notice some seasonal patterns here. Since our data set is for 1 year, okay, just let's just try and look at whether we have similar data points here. Okay, we have only this portion. Okay, we have the same month only here. Okay, so we have August and August, but very little data to actually draw conclusions about this. But generally, if you have data which has not been seasonally adjusted, you'll find that in the same season, you might notice a similar pattern across years. Okay, since our data set is still relatively small, even though we've used daily data, we have around 250 odd observations. Okay, so it's not enough to draw conclusions about the seasonal pattern probably because I don't have too much data for the same months across the years. So here you might notice some similarity here, but not enough to conclude. But generally, if you have a data set and you have the same 2 seasons in different years, okay, you might notice the same seasonal pattern. For example, there might be a sharp spike in sales in some holiday season or a festive season or something like that. Okay. So this again, we'll take a look at it in greater detail later, okay, when we're actually doing tests of stationarity. Then another thing here, if you notice the returns, okay, this is the simple net return, this is the log return. So if you look at the values, they are more or less the same, okay, very small differences or slight differences between the two values. So you'll, if I plot it also, you'll be able to see that. All right, so this orange line, it denotes the continuously compounded or log returns. Okay, so you can't even see the simple returns here. Okay, now if I just try to, let's say, eliminate this, okay, then you get the simple returns. Okay, so you can see that there was a very close overlap, so we couldn't even observe the simple returns in the graph. Okay, so they are very close, the two values are very close together. Probably if you have a larger data set, it will be more interesting to do more analysis.
Ma'am, I have a question.
Yeah.
Ma'am, so as we know that variance is a very concerning thing when it comes to the stationarity of the data in the time series analysis. So is there any concern for bias also? Like variance and bias are related to each other, like they are inversely proportional to each other. So is there any concern for the bias in the time series analysis, as these both are the concern in the regression analysis, but is there any concern in the time series analysis for the bias?
See, the main reason that we look at whether the mean is constant, variance is constant, and so on, it's basically because if our time series is not stable, okay, or if these parameters keep fluctuating constantly or they're not reliable, then the main thing that we're usually interested in is forecasting or prediction. Okay? So if you can't use the information in your series to reliably predict the future, okay, then the whole point of your analysis is lost. That's why we look for a constant mean and constant variance in our time series. Okay, because if you are sure that the series has a constant mean variance, it is more or less stable, then you are able to predict the future generally based on the past. Okay, or you can be sure that there will be a stable relationship of that particular variable with, if you're using other variables to predict it, you'll be able to predict with a greater deal of accuracy because your entire data set is somewhat stable. Okay, the parameters of that are not fluctuating too much. So you can use the information from that data set usefully or reliably. Okay?
Ma'am, I have a question.
Yeah.
Ma'am, as you said that variance is necessary, but it can be removed or adjusted. But isn't every data that you take into account for prediction includes variance? Because there is seasonality, there are trends, there are unusual events, there are outliers. It is part of data. So if we remove it, aren't we predicting wrongly? Because it's impossible to do so without taking into account stationarity and seasonality, ma'am.
Okay, one thing, I'm not sure if I understood your question right, so I'll just explain a little bit again. Okay, so I don't think I mentioned that we should get rid of the variance. Okay, we are not trying to get rid of the variance, but you need to address seasonal patterns, okay, in your data. See, any time series, you all have probably learned it, okay, already. It can be divided into different components, right? Okay, what are those components? You can break down or decompose a time series into 4 components. What are those components?
Trend, seasonality, cyclicity,
Yeah.
and one more.
Outliers.
I forgot.
Sorry. Yes, ma'am.
Yeah, irregular.
Yes, ma'am. Irregular.
Yeah, irregular component or the random component. Okay, so any time series, it can be broken down into these. Now, generally, for the previous graph that I showed you for Infosys returns, you found that the trend is there, right? Okay. Now, when we took the returns, basically we were eliminating that trend over there, and that helped us analyze the data. Okay, that's something we'll do probably next week. We'll actually analyze and use that data. Okay, but generally, if you want to work with data, you'll try and eliminate that trend or make sure that the mean of your series is constant, or basically it has mean stationarity. Okay, we want our series to be stationary and then we start working with it. So the first step of any analysis is always to ensure that your series is stationary. Okay, before you check for stationarity and so on, you have to keep your data in such a form that it is ready for testing. Okay, even for stationarity. So usually we eliminate the seasonal component. So you seasonally adjust your data so that those seasonal patterns are eliminated. Okay, why do we try and eliminate the seasonal patterns? Because those patterns are predictable. Okay, every season you are able to see that particular pattern. So you'll probably not have any other useful information except for the fact that in that particular season you notice a spike in sales or something like that. Okay, so any time series, it can be decomposed into these components: the trend, the cycle, then the seasonal component and the irregular component. Okay, so trend, we can detrend the data by just taking a difference or growth rates. Okay, then for the seasonal part, there are methods to seasonally adjust the data. Okay, for example, you can decompose your data into all these components and then remove the trend from it. We'll try and do that next week. Okay. Otherwise, there are procedures that are inbuilt in the software, okay, like X11, 12, and so on. So that helps you actually do seasonal adjustment with a simple command. Okay, you don't really have to fit a model or anything like that because it's already inbuilt. So generally the data is seasonally adjusted because those seasonal patterns are not very interesting for us, okay, in our analysis, unless you're actually trying to predict seasonal sales or something like that. Okay? Now the next part, the cyclical component. Okay? Now the cyclical component, these are basically irregular fluctuations. They are not periodic. Okay, the cycles, they are not predictable, but they are fluctuations probably around the mean or the trend of your business activity or the normal activity. Okay, so generally, again for this, you have methods to remove the cycle. Okay, generally when we are working with data, we might not remove the cyclical component also, but there are also methods to remove the cycle. For example, by decomposing, what we'll probably do that next week. The other methods are you can use filters and then remove the cycle. Okay? And whatever is left after removing these first three components, if you remove the trend, if you remove the seasonal component, and then the cyclical component, okay, that you will find gives you the irregular or your random component. So whatever is left, the residual is this random component. Okay. Now we generally don't try to explain this or predict this random component. Okay. So we are interested in the other three components and we use them based on what sort of analysis we need to do. We might remove the trend. In some cases, you might want to work with the cycle itself if you're studying business cycles. Okay? And seasonal adjustment we do with almost every data series. Okay? So you'll find that these sort of adjustments are made. So I'm not saying that we are removing the variance here. Okay? You're not removing the variance, but basically you're trying to make it constant. Okay? You're trying to ensure that by some sort of transformation of your data or manipulation of your data, you are able to bring it to a stationary form so that you can use it for more analysis, so that you can use that for prediction, for forecasting purposes, for policy purposes, and so on. Okay? Because otherwise your data will not be reliable. I hope that answered your question. I'm not sure if I understood your question right, but I hope I could answer it.
Yes, ma'am.
Okay.
I got it.
Yeah. Okay, so we'll just come back to this. This is another data set. So you can see that this is GDP by expenditure. Okay, this is for India, and this has been seasonally adjusted. So this was what I was talking about. In some cases, you'll find that the data is available. It's already been seasonally adjusted. In others, you'll have to make the adjustment yourself. Okay, so this is quarterly data from 96 to, I think, the latest data. Okay, so let's just plot this and see. Okay, so again, for this, you can see an upward trend here for GDP. You can see this dip over here. Okay. Now this series also, just by looking at it, I'm sure you can tell that it is not stationary. Okay, because the mean is changing over time. If you take two different slices, okay, of data, okay, the same two slices of data, then you'll find that the mean is changing. If I take one portion over here, okay, and the same size window of data or sample subsample of data, again you'll find the mean is changing. Okay, so this is clearly not mean stationary. Okay, so since the first condition itself is violated, we can conclude that it is not weakly stationary. Okay. Now about variance, again, we might not really be able to draw a conclusion since this is quite a lot of data. Okay. So we might not be able to tell very easily from this. Okay, now what I've done next is here I've basically taken the log growth rate. Okay, and then let's just try and look at this. Yeah. Okay. So based on this, you can see that once we use growth rates, okay, we've used a transformation of this data itself. So now we've been able to make the series stationary, okay, except for this little blip here. You'll find that it's more or less fluctuating about this value. Okay. And the fluctuations are also more or less constant. Okay. You can't see very high spikes anywhere or very large deviations from the mean anywhere. Okay, so you'll find that you have almost the same size fluctuations everywhere except for this part. Okay, so generally growth rates you will find are stationary. Okay, whereas if you take the raw data itself, if you take raw GDP data, you will find that it's not stationary. So in many cases, just like how we do in financial data, we don't use the prices itself. Instead, we use the rate of return. Okay, so that is also basically a growth rate. So generally, we use this first difference transformation. Okay, so if you were not taking the log growth rate, you'd just basically be taking GDP at time t minus GDP at time t minus 1 by GDP at time t minus 1. Okay, that would give you a growth rate into 100. The same thing, I've just used the log growth rate here. Okay. So if you take this sort of first difference transformation, okay, if you take PT by PT minus PT minus 1 or GDPT minus GDPT minus 1, okay, generally that brings the data into a stationary form. We'll do that probably next week, okay, when we are actually doing the practicals. But by using these sort of transformations, we are able to get our data in a stationary form, and then we can go ahead and work with it. So have you all understood this concept of stationarity?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Ma'am, just a question.
Yeah, somebody has a question.
Yeah. So, ma'am, you said that we need to apply some sort of transformation to actually introduce stationarity to the data, right? So,
Yeah.
can you give an example of certain methods that we can use apart from the log function?
Yeah, log function, there again I took the first difference. Okay, so if you take a variable at time t, subtract its value at time t minus 1, that's called a first difference transformation. So that is the most commonly used method. Then you can find a similar thing for if you have seasonal data. Generally you take the same point in time. Okay, so for example, if you have quarterly data, okay, so you'll take let's say quarter 1, okay, in 2021 minus the value in quarter 1 2020. Okay, so this sort of transformation is also used. This is again a difference transformation, but you're using the same point in time in the previous time period. Okay, the same season in the previous time period, you're using that sort of a transformation. Okay, so generally this is the most common first difference transformations are the most common, working with growth rates or returns. Okay, other transformations we'll try and look at when we are actually working with data. You'll understand that better there. Okay, but in general, these are the most common ones which are used. So we'll come back to what we were discussing in the previous class. Okay.
Ma'am.
So here, once you are,
ma'am, your voice is coming a little muffled. In the middle, it had become very clear. I'm not sure what is the mic issue.
Okay, probably some issue with my net connection. Right now, is it clear?
Yes, ma'am. It is clear.
Okay. So we'll move on. Okay, so this is about stationarity itself, and then we discussed a white noise process, okay, where a white noise process is stationary because it satisfies all those conditions, but it has the peculiar characteristic that the mean of that series will be equal to 0. The variance will be some constant sigma square. And the covariance again is independent of time. Okay? So you'll find that there's no linear dependence between the series at time t and its lag. Okay. Now I think we had stopped at this point yesterday. Okay. So generally we use the covariance and the variance, okay, to come up with a measure known as the autocorrelation function. Okay. So now if you look at the formula carefully, you'll probably notice that it's basically your correlation coefficient, okay, that we are calculating. But since we are looking at the correlation or linear dependence between a particular time series and its own past values, okay, so that's why we use the term autocovariance or autocorrelation function and not correlation function, okay, or not correlation coefficient. So this is called the autocorrelation function or coefficient at lag tau, okay. So this gives you the formula for the autocorrelation function at lag tau. So you can calculate this for any lag. For example, if I take the first lag here, this will be rho 1, okay. This will be xt and xt plus 1, okay. So you're looking at, if you look at this as the lead, okay, since we are putting a plus sign here, this is the lead and this is the past value of this xt, okay, xt plus tau, this is the past value of xt plus tau. So basically you're looking at the linear dependence between a series and its own past values, okay. So here also, since we are assuming that the variance is constant or finite for the entire series, okay, you will find that you can simply take expectation of t minus mu, okay. You don't have to take, even if you take expectation t minus mu and then again xt plus tau minus mu, since the variance is the same for both, it finally reduces to this, okay. So here this gives you the formula for the autocorrelation function. Okay, so yesterday I had stopped at this point and I asked you, this gives you the covariance at lag tau. This is the variance at lag 0. Okay, since lag 0, because if you put 0 here, you'll simply get the variance in the formula. Okay. So here I had asked you what is the utility or use of using this measure of an autocorrelation function. Why can't we simply use the covariance itself to understand linear dependence of a time series on its past values?
Ma'am, because if we take covariance of the, let's say, S&P 500,
Yeah.
we'll get a number in thousands. And covariance will allow us to compare, for example, if, for example, I'm getting a higher covariance with a certain period, I know that these two periods are more strongly correlated. But when we divide it by the variance, we are basically standardizing it from -1 to 1. So we actually know the strength of those correlations. So we can make relative comparisons.
Yeah. So here basically, since the covariance, it is not free from the units of measurement. Okay. Whereas when you're using this autocorrelation function, you'll find that it is free from the units of measurement. Okay. So you can easily use it to understand what is the strength, like he said, of the linear dependence or association between a variable and its own lags. Okay. Whereas covariance, it will be very difficult to understand it because it's not free from the units of measurement. Okay. So generally, that's why we work with the autocorrelation function. Okay. Now, the ACF has the following properties. Okay. This, I'm sure all of you are aware of this already, but we'll quickly go through this. Okay. So, rho 0, okay, at lag 0, it will be equal to 1. Okay, this is because if you take 0 here, it's simply the variance by variance, so it becomes 1. Okay. So the autocorrelation function at lag 0, it has a value of 1. Then this function is also symmetric. Okay, so whether you're using leads or lags, okay, the function will be symmetric. You'll get the same value of the autocorrelation function. Okay. Then this autocorrelation coefficient, it is bounded between the values of -1 and +1, okay, for all time or for all the observations. Any doubts regarding this? Anything that you haven't understood? Okay, so we'll move on.
Ma'am,
Yeah.
do we make an assumption that tau is much smaller than the number of data points we have?
Yeah. Okay. So generally, you won't for example, for the first observation, you will not have a lagged value, right? Okay. So generally, when you're writing what is the index for tau, okay, you'll generally find that you don't have the first lag is not available for the data. Okay. But when we're writing this, generally it's so that you can understand that we're using leads and lags. If you put it into the formula, here if you're putting negative values, you're taking lags. If you're putting positive values, you're taking leads. Okay, but yeah, your point is valid. If I understood it correctly, then it's valid. Now for the sample, okay, you will find that this is how you can calculate the sample parameters, okay, or the sample estimates or statistics. So here, this gives you the formula for the mean, then variance, okay, for the sample. Then this is the covariance for the sample at lag tau. Okay. This is what you were talking about, right? The person who asked the previous question.
Yes, ma'am.
Yeah. So this will give you the covariance at lag tau. Okay, and all these are supposed to be consistent estimators of the population mean, variance, and covariance at the same lag. Okay. Now for the sample, since we have to work with the sample itself, we usually calculate the sample autocorrelation function or sample autocorrelation coefficient. Okay, so this formula can be used for this. Okay, and we find that in general, the sample autocorrelation function is asymptotically unbiased. Okay, so as the sample size grows larger and larger, it becomes a consistent estimator or it converges towards the population parameter. Okay. Now there are certain tests.
Could you repeat that point? I'm so sorry.
Yeah, basically as the sample size grows larger, okay, tends towards infinity, you will find that the sample autocorrelation function or coefficient, it will converge towards the population parameter value. Okay.
Okay, ma'am.
Now, generally, whenever we are doing any sort of modeling work, okay, especially after we have estimated the models in finance, sometimes we use this right at the beginning. Okay, but generally we need to test for the autocorrelation. Okay, so there are certain tests that we use, and the basic idea is we want to test whether several autocorrelation coefficients are simultaneously or jointly equal to 0. Now, if you estimate models, for example, after we complete this first lesson, okay, which is based on your ARMA models, autoregressive and moving average models, or ARIMA models. I think sir was talking about this in the first class. Okay, so once we've estimated those models, usually we need to check how well those models are performing. So we check the residuals or errors from that model, okay, the error terms from that model. And if the error terms are found to be uncorrelated, okay, then the model is supposed to be satisfactory. So generally we carry out such tests and we want to know whether all the autocorrelation coefficients are simultaneously equal to 0 or jointly equal to 0. Okay, so several tests have been developed for this. Okay, so one such test was developed in 1970. It's called the Box-Pierce test. Okay, so here, this is the statistic for the test, okay, where T is your sample size or the number of observations that you have. Okay, M is how many lags you want to take, okay, or how many autocorrelation coefficients you want to estimate, basically. Okay. So here, this gives you the sample autocorrelation coefficient, and this statistic is distributed according to the chi-square distribution with M degrees of freedom. Now, the null hypothesis for this test is that all the autocorrelation coefficients are equal to 0. Okay? So there is no linear dependence between the variable and its past values, okay? Or that the errors are uncorrelated, since we usually work with errors. Okay? The alternative hypothesis is that some of the autocorrelation coefficients are not equal to 0. Okay? So some could be equal to 0, but some will not be equal to 0. So there'll be some sort of serial dependence or serial correlation here. Okay, so this is one particular test which is used. So we'll be doing some of these tests also. Okay, these two we'll definitely be doing. Then another test is the Leung-Box test, which was developed in 1978. So basically what they did was they took this same statistic and they modified it so that it will perform better when you're using small samples or finite samples. Okay. And this is the statistic. Okay, so you're taking a summation of this entire term here. Okay. That might not be clear the way I've written it, but this is the test statistic. And again, this is distributed according to the chi-square distribution with m degrees of freedom. It has the same null and alternative hypothesis. Okay, so wherever you find that the value of the test statistic is greater than the critical value, you will reject the null hypothesis, okay, for both the tests. Then the third test that we can use is the Lagrange multiplier test. This was developed by Bruce and Godfrey, so this might be familiar to you all. Okay. Have you all studied this when you're studying the violations of OLS? Violations of the assumptions of OLS, you might have studied this. Does anyone
We've
remember
studied
it?
the BP test, Bruce-Pagan test.
Okay, yeah. Okay, so this, for this, basically what you need to do is estimate your model. Then for this particular test, this is the test statistic. Okay, the R square from that regression, and this gives you the sample size or number of observations. Now this again follows the chi-square distribution with p degrees of freedom. Okay. Now when you're running this test, basically you have to carry out an auxiliary regression. Okay, so what you do is run the initial regression, from that extract the errors or the residuals, then regress those residuals on the explanatory variables from your regression model. Okay. Along with the explanatory variables, you will also regress the errors on the lagged values of the errors, okay, up to some order p. Okay. So you will find that by carrying out such an auxiliary regression, you can carry out this test here. Okay. And the null here is that all the autocorrelation coefficients are jointly equal to 0. The alternative is that the residuals follow an autoregressive or moving average process of order p. Okay. So basically there's some serial dependence or linear dependence of the errors on their own past values. Okay. So in
Ma'am,
that,
are these tests of stationarity?
no, not for stationary.
Then these are tests to understand what exactly?
See, basically, once you run these tests, okay, yeah, in some sense, they are stationarity tests itself, because you're checking whether your errors are stationary. Okay. So if you find that based on these tests, you're not able to reject the null, okay, then in all the cases, since these autocorrelation coefficients are equal to 0, basically it shows you that your error terms, or the time series of errors or residuals that you have, they are white noise processes. Okay? Since they are free from any sort of serial correlation or dependence. If you remember, for a white noise process, okay, the covariance between the errors and its lags is equal to 0. So in some sense, yes, it's a stationarity test, but this is mainly to check whether a series is white noise. Okay. Now, have you all studied the Durbin-Watson test when you all studied basic econometrics?
Yes, ma'am, I think we've studied it.
Okay. So here now the advantages over the Durbin-Watson test itself.
Ma'am, I would just like to say that there are two classes out here, FE and IBEF. FE and
Okay.
IBEF both are different teachers for econometrics.
Okay. Have both batches, I mean both classes, have you all studied Durbin-Watson test?
In FE, it was discussed once. I don't know about IBEF.
Okay. Anyone from IBEF? All right.
Ma'am, if you could briefly cover them once again, it will be very helpful.
Okay. What we'll do is, since that will be coming up a little later again, okay, but if you want to test for first order autocorrelation, basically we use the Durbin-Watson test. Okay. Now the particular test, you basically regress an error on rho and t minus 1. Okay. So in that particular test, you'll notice that, sorry, I said rho and ut minus 1, okay, not just t minus 1. So ut is equal to rho into ut minus 1 plus some error term, okay, et. Now generally, if you look at the nature of that test, you are only checking for autocorrelation of the first order, okay, since you're regressing the error term on its first lag only. Okay? So you can only check for autocorrelation of the first order. So you're only able to check whether a variable is dependent on its first lag. Okay? You're not able to check for higher order dependence using the Durbin-Watson test. Now, there are some modifications of this test, if I remember it right. You cannot apply it if your model has lagged endogenous variables. Okay, so for example, if your dependent variable is yt and in your list of explanatory variables you have yt minus 1, yt minus 2 and so on. Okay, in that case, you will not be able to use the Durbin-Watson test, whereas you can still use this test, the LM test, yeah? Lagrange multiplier test.
Ma'am, you can't use Durbin-Watson, but you can use Lagrange multiplier when you have lagged endogenous variables.
Yeah, that's what I'm saying.
Oh, but the sheet says advantages of Durbin-Watson is it can be applied in case of lagged endogenous variables.
No, it says advantages over. Okay,
Okay.
how is it better from using the Durbin-Watson test?
Thank you, ma'am.
Okay. So, yeah, but if you notice that I've written something wrong, please point it out to me, okay? Because I might be writing in a hurry, so I might not write it correctly, like what happened yesterday. So if you find any error, then please bring it to my notice. Yes. Yeah, another test. Okay, I've given the formula again over here because it is relevant to this. Okay, another test that we use for testing for normality, okay, is something known as the Jacques-Bera test. Okay, I don't know how many of you all know, but this person is an Indian. Okay, so it might not make a difference to you all, but it was just interesting for me to know that this person is an Indian in the Jacques-Bera test. So this is the test statistic for the Jacques-Bera test. This is the number of observations. M is the number of estimated parameters. Okay, so how many parameters you're using to run your regression. Then this is the value of skewness and kurtosis that you're estimating from your sample. Okay? So now this statistic also follows the chi-square distribution with 2 degrees of freedom. And the null hypothesis of this test is that the variable is normally distributed. Okay? The alternative hypothesis is that it is not normally distributed. So generally, you'll find that after carrying out any regression, okay, you'll be running these sort of tests. You usually check if your errors are white noise. If they are white noise, it means that your model has performed satisfactorily. And you'll also want to check whether the errors follow the normal distribution. Okay, these are generally tests, diagnostic tests to run after your regression. That's why all these tests are mentioned over here. Okay. Now it's almost 3:30. We'll take a quick break. Okay. We'll meet in 5 minutes, and after that we will resume. Okay. So just 5 minutes. It is 3:29 by my watch. So we'll meet at 3:34. All right. So shall we resume? It's 3:34. I hope you all are back. Am I audible to you all?
Yes, ma'am.
Yeah, okay. One more thing I just remembered, for Durbin-Watson test, okay, we don't directly test rho itself. Instead, we take ut is equal to delta ut minus 1, okay, where delta is equal to 1 minus rho. So we usually test it indirectly. So now if delta is equal to 0, which is the null hypothesis, it will mean that rho is equal to 1. Okay, so there's perfect first order serial dependence between ut and its first lag. Okay, so that is how we test it usually. We don't take rho directly, instead we take delta, where delta is equal to 1 minus rho. So we'll continue. So now for any time series, am I audible to you all?
Ma'am, I have a doubt here.
Yeah.
Ma'am, for the white noise, shall we not, like, should we not perform the white noise test before we get into our regression? Like, first, if we first of all know if our data is white noise or not, then it will be better if we then like go on to regression model.
See, usually when you're working with data, what are the characteristics of white noise data? It has a mean of
0.
0. Yeah, and the variance is constant. Okay, so generally whatever data series you're working with, it might not have a mean of 0, right?
Yes.
Okay, so generally we don't test outright for white noise initially. There are some cases later on we'll deal with it when we're looking at arch models and all, where we carry out this test right at the beginning. Okay, but some sort of this kind of a test. But generally, since the focus is on the errors from your model being white noise, usually the tests that I just mentioned, they are carried out after your regression.
Okay, so like white noise is basically for our error terms after we have predicted our model.
Yeah, generally in whatever models we write, you'll find that even here when we're discussing. So generally in time series, when you're writing the model equation, you'll find that the error term, you'll make certain assumptions about it, right? So there, when we are
Yes.
making the assumptions, you'll be assuming that the error term is a white noise process. Okay, that helps us in our analysis when we are coming up with the derivations and all that. So for that purpose, we generally use the assumption that the error process follows is a white noise process.
Okay, ma'am. Got it. Thank you.
Yeah, so we'll go ahead with this. Now for any
Ma'am, I have a
time
doubt.
series, yeah.
So, ma'am, when our resultant error term is white noise, that means that our model has been optimized correctly. We have correctly optimized all the ARMA terms, right?
Optimized in the sense that our model is free from any sort of specification errors, okay, that the model is sound. Yeah. As in, there's no other specification which would have been a better fit, okay, for your to describe your data.
Yeah, I got it, ma'am.
Okay. Now for a wall decomposition, generally any stationary time series, okay, any time series itself, it has a certain linear representation, okay, or it is given a general representation, and this representation is called the Wald decomposition. It was proposed by somebody named Hermann Wald. Okay, he was working on his PhD thesis, interestingly, and he came up with this decomposition. So this decomposition, it exists for every covariant stationary, purely non-deterministic stochastic process. Okay, so I'll explain what this means, but just think that for any time series which follows the conditions that we just discussed of weak stationarity, okay, you can represent this time series by using such an equation or such a decomposition. Okay, we'll look at what exactly this decomposition is. Now, when we are using this word here, okay, purely non-deterministic stochastic process. So here, any process, if I take this equation, okay, the one that I'm circling here, if I write it in terms of xt is equal to mu plus this term, okay, then it is a deterministic stochastic process, because this mu, we are going to assume that it is constant and so on. Okay, so this mean part is deterministic. Okay, so that makes it a deterministic stochastic process. This part is still stochastic. Okay, but once I subtract this deterministic component from the time series, xt minus mu t, okay, then what I get is a purely non-deterministic stochastic process. Okay, so that's what this means. If I write any time series in this form by subtracting the deterministic component from it and writing it in terms of the errors, okay, or a white noise process, then that time series has this wall decomposition, or it can be represented using this wall decomposition. Okay? But basically what it all boils down to is that this time series will have can be written as a linear time series, okay, or it can be represented as a linear time series. Now, when we are writing this equation, we are making certain assumptions here. Okay? So one is that psi 0, okay, is equal to 1. So if I write 0 here, okay, first j is equal to 0, that value will be equal to 1. The other assumption is that the sum of the squared psi j's is finite. Okay, there's a finite sum, it is not infinite. We also make the assumption that UT is a pure random process, or basically a white noise process. Okay, so these are the assumptions that we're making about UT, that its mean value is equal to 0, expectation UT is 0, then its variance is finite and constant equal to sigma square. Then the covariance for T not equal to S is equal to 0. Okay? So there is no serial dependence between the UTs, or no linear dependence between the UTs. So now if we take expectation of this, okay, xt minus mu t, okay, then we get that value is equal to 0. Since we have assumed that expectation of ut is 0, so the expectation of all the ut minus j's will be equal to 0. Okay? So from this, we can conclude that expectation xt is equal to mu t, or the mean of xt, this time series, is equal to mu t. Okay? So far, is it clear to everyone?
Ma'am, I'm so sorry, could you please repeat the why are we, so ma'am, are we going to check for every term separately and then see if it holds to 0?
You'll see once we get the mean, we've extracted the mean now, next we'll get the variance. Okay, after that we'll look at the covariance. Do you want to wait and then ask your question, or?
Yes ma'am, I'll wait.
Okay.
Ma'am, I also had a doubt.
Yeah.
I just got a bit confused.
Hmm.
Where did we got this UT from? I
Mm,
mean, what was the process? Was there any regression? Because suddenly it struck me.
no, there's no regression. This is basically a theoretical construct, okay? And we'll be using it in the next few parts of our discussion. That's why this is important. Now just think that any time series, it can be written in the form of two components, okay? One is this deterministic component, the other is the stochastic component. Okay? This is something good that you asked this question. This is something that I forgot. Now, the reason that we are interested in this decomposition is that these parameters here, okay, these coefficients psi j, they basically are the weights that you attach to the error terms, okay, or these UTs. And these UTs are generally called an innovation or a shock. So if you look at any regression model, right, you have the error term, and that basically captures all the omitted variables, or all the things that you can't explain based on the model that you have constructed or tried to fit. Okay, all those things are captured by the error term, right? Now in this case, Okay, the error term, it talks about the innovations or shocks. Okay, so once you write an equation, what is the shock to the system which will probably lead it to along a particular path? Okay, that's what we are interested in. So these UTs are called shocks or innovations. Okay, and these psi j's are basically the weights attached to these innovations. Okay, so you will find that any time series, once we go to the latter part of the discussion, we'll see that, okay, what it actually means. But basically these psi j's, each of them will converge towards zero, okay, as you progress in time. For example, for j is equal to infinity, okay, you will find that the psi j's are very negligible in terms of the weight, okay, or the value of the psi j's. They'll be very close to zero or actually zero. So what it means is that for any time series, the past, especially the distant past, will not have much of an impact on the time series. So in terms of linear dependence, the very distant past or very extremely lagged values, okay, large lags or very lags in the distant past do not have much of an impact on the current value of a time series. Okay, so usually the whole idea behind time series analysis is generally, especially ARIMA modeling, is you're using the past to predict the future. Okay, you're using past values and patterns to predict what is happening in the future because you think the past predicts the present and that will help you predict the future also. Okay, so here when we are writing this or using this representation, we generally assume that these psi j's, as the sample size keeps getting larger and larger, or you go into the distant past, okay, as you go back into more and more lags, you can see they are attached to the lags of the innovations. Okay, so as you go into the distant past, the impact of those shocks or innovations will become less and less and they'll gradually fade out. Okay, so that is the relevance or the reason why we use these psi j's or these weights. Okay, is that okay? Have you understood?
Ma'am,
Yes, ma'am.
Yeah.
This is basically showing that autoregressive process, right? The coefficients keep on getting multiplied and keep on getting smaller and smaller until they become insignificant.
Yeah, we'll come to that in the next part. Okay, so just wait a little. So far we've come to the mean. Okay, after that we'll look at the variance, then covariance, then we'll go into the autoregressive models or autoregressive processes. That's where what you're trying to say will come in over there. Okay?
Yeah, thank you.
So next we'll look at the variance. Okay, so the variance again, instead of xt minus mu t, we just use this. Okay, we use this. So expectation of that term, okay, the whole square. So once you expand the term, this is what you will get. For j is equal to 0, okay, psi j, when j is equal to 0 is equal to 1. Okay, if j is equal to 0, you will get ut. So it will be 1 into ut. Okay, this is what you got here. Similarly, you keep expanding the terms. Okay, so psi 1, if j is equal to 1, it will be psi 1 ut minus j is equal to 1, so you get ut minus 1 and so on. So you keep expanding the terms. Okay, take the square of this whole summation. Okay, so then each of those terms you'll be taking the expectation of each of those individual ut squares. Okay, so you finally end up with this. Now this gives you the variance of xt. Okay. Now you can see that the variance of xt is not dependent on time. Okay, there's no variable here which depends on time here. Okay, so this is some parameter, some constant, okay, and this is some constant. Okay, so this is independent of time. The variance is independent of time. Okay. Then
Ma'am, can you
next.
scroll up for a minute?
Yeah.
Thank you, ma'am.
Then next we look at the covariance. Okay, so you're looking at the covariance between xt and xt plus tau. Okay, so here you're taking a lead, but the covariance again should be symmetric. Okay, so here just look closely at the formula. Okay, if you don't understand something, you can tell me. I won't read it out, it will not make sense. So basically here you're expanding that term. Since xt minus mu t is equal to summation j is equal to 0 to infinity psi j ut minus j. Okay? You're expanding that term. Then similarly for this, you'll be expanding this term. Okay? For the second bracket also, you'll be doing the same thing. So if you've looked at this part, now for the next line of this derivation, basically here, since expectation ut is, I think there's another ut here, yeah. Yeah, so here you will get, since these two terms are ut, you will get expectation of ut square, okay, and sigma square. So that is your first term. Then all the cross products vanish. Okay, for example, if you take expectation ut and ut plus tau minus 1, okay, that is going to vanish. Or expectation ut and ut plus tau is equal to 0, right? Those are the assumptions that we made about ut. Okay, so the cross products will vanish. You will be only left with ut square, okay, then ut minus 1 square and so on. Okay. So if you bring sigma square out as common, then you'll be left with these psi parameters or coefficients. Okay, so this is this line of the equation. Then you're just summing the psi j's in the next line. Okay. So this basically formula gives you the covariance between xt and xt plus tau. Okay. Now the covariance of xt and xt plus tau is finite. Okay, this is again because of the sort of assumptions that we have made. Okay, we have assumed that sigma square is some constant. In addition, that we have assumed that the sum of the psi j's is less than infinity. Okay, so because of the sort of assumptions that we have made, you will find that the covariance is finite. Okay. Now next we use this equation and the formula for variance. Some of you might be seeing stars, so the next part we'll try and look at this, okay, how exactly we got this, if it's confusing for you all. Now rho tau, okay, this is the autocorrelation function or coefficient at lag tau. Okay, so between xt and xt plus tau, we are looking at the autocorrelation function or coefficient. So here this gives you the covariance. Okay, if you take the covariance and the variance divided by the variance, you'll be left with this, since the sigma squares cancel out. Okay, so you'll be left with this term here. Okay. And all stationary models can be represented on the basis of this Wald decomposition. So if you take any stationary model, you can probably break it up and express it in terms of the errors by removing the deterministic component and then finding the mean, variance and covariance. That will help you find the autocorrelation coefficient finally. Okay. Any doubts? You all might be a little confused about the notation here.
Ma'am?
Yeah.
Why ut is assumed as 0?
Where is it assumed as 0?
Expectation of ut is equal to 0.
That we have assumed it is 0. We are assuming that it is a pure random process or white noise process. So the characteristics of that process itself are that expectation ut is equal to 0. You
Okay.
want to go into the derivation of that, is it?
Yeah, I'm not getting why it is assumed like.
Okay, just for now, just think that you have assumed it, so you will work with those formula or formulae for now. Okay.
Okay, ma'am.
In the
Ma'am,
next,
this.
yeah.
Yeah, yes, ma'am. You can continue what you say.
No, just note down any of these doubts that you have. For example, this. Okay, so if there's any other explanation, then maybe when we're covering MA processes, you'll see that a little more clearly. But basically, it's an assumption that we make. Okay?
Ma'am, what is this rho tau? This is.
Rho tau, this one is the autocorrelation function or coefficient. Okay,
Okay.
remember that we calculated covariance of xt and xt plus tau by variance of xt gives us the autocorrelation coefficient of function. This is for the sample, this is for the population. This same thing we are using there. Okay, you took the covariance, divided it by the variance. That's how you got that final answer. Okay, so just to maybe help you clarify how we got this notation here, okay, it will be helpful for you all itself if you all do it. Okay, so just try and use this formula, all right, and take tau is equal to 2. Okay, I've worked it out. That's why I want you to take this particular example so that you can see for yourself whether you've understood it. Take tau is equal to 2. All right, and start with the value of t is equal to 5. Okay, so t will run from 1 to 5, but when you're taking t here, the value of t, take it as ut. Here the t will be equal to 5. Okay, and then proceed that way. Does anyone want me to repeat what I just said? Have you all understood? Yes or no? Am I audible to you all?
Ma'am, one doubt I have.
Yeah.
When we are estimating this rho t as we are decomposing it into some weights which are attached to each error terms, right? That's how we are looking.
We are decomposing xt, which is our time series.
Yeah, and rho t works out to be equal to those, a ratio of those weights.
Yes.
So in practice, we actually directly estimate rho, right? Not the weights.
No, this is what we are doing right now is a purely theoretical exercise.
Yeah,
So
that's
there's no practical application of this. This is just a theoretical exercise because we'll be doing some things which are related to this in the next portion.
yeah, fair enough. My doubt was actually these weights unique, or you can have combinations which whereby the same row can be arrived at by different combinations of weights.
I'll have to think about your question because I need to process it a little. While you'll work that out, I'll just think about it. You're saying that can you have a combination of weights?
No, all I'm saying is it's possible to decompose in a particular way, but looking at that formula, I'm not a maths guy actually. Okay. I'm just trying to look at it conceptually. So since these are set of numbers, they may not be unique. So decomposition can happen in possibly different ways. That was my just doubt. Again, a theoretical doubt for a theoretical construct.
Okay. I'll have to think about it. Meanwhile, if you all can just work on this. All right. So just take tau is equal to 2. Am I clear to everyone? Take tau is equal to 2 and start with t is equal to 5. Okay. So your t is running from 1 to 5. So the first term here, expectation ut, this part will be u5. Okay. And then proceed in that way. Sorry, I mean your j is running from 1 to 5. Okay? J is running from 1 to 5. Are you all doing it, or you all didn't understand, or?
Ma'am, I'll be honest. I think after the ball decomposition, we got a little confused.
Okay.
I don't want to speak for the class, but I do think that might just be true.
Yes, ma'am. Me
Okay,
too.
wait. Okay, let's backtrack then.
Ma'am, instead of backtracking, can we see how these are used? Then we'll understand what each of these mean. Because, ma'am, just going over this might not put it into our head, but rather if we see these in action, or if we see these tests happening on some R or on Excel or on
Yeah,
Python, then
that's exactly why I was telling you that it's a theoretical, purely theoretical exercise. Okay, you can't go and do this in R, and or it'll be extremely cumbersome. Okay, and I'm not the person to do that. But I don't know of it being applied in practice. Okay, so this is purely a theoretical exercise, and in the next portion that we are dealing with, when you're doing AR processes, you'll be dealing with these sort of derivations. Okay, so that's why we are going through this right now. So if you're stuck at this point, we won't be able to proceed. So just try and take a look at this again, see if you can understand.
Ma'am,
Yeah.
I had a doubt. Basically, this wall decomposition is showing us an autoregressive process, right? It shows that X is made up of some deterministic component UT, and and is lagged on the errors of the previous terms. For example, it's dependent on UT minus 1, UT minus 2.
Yeah, yes.
And these psi's are in a sense coefficients. They're coefficients, right?
Yeah, they are coefficients, and basically they are telling you what is the weight attached to the past shocks. Okay, just think of a
Yeah,
series,
and
or
these psi's are eventually converging.
yeah, okay, just think of some object, maybe think of a ball placed on a table, and imagine that it's placed at a single point, and then you take a stick and hit it with a certain force. Okay,
Yeah, this is
so it
basically,
moves in a
ma'am, a decaying
particular,
signal, right?
yeah, sorry.
This is a decaying signal, right?
Yeah, yes,
In a
yes.
signal process, the signal keep on decaying as
Yeah.
the process goes on.
Yeah.
Okay.
So basically, what I'm trying to say is the impact of past in the distant shock. Impact of shocks in the distant past. For example, if I take UT minus 10, okay, so I'll expect that to have a lesser impact than UT minus 1. Okay. So the impact will progressively become smaller and smaller as you go into more distant lags. Okay. Compared to the first lag, the 10th lag or 15th lag will have a lesser impact on the time series than the lags in the more recent past. Is that clear to you all?
yes, ma'am, that part is clear.
Okay. So just take the example of that ball itself, okay, that you've placed on the table. I'm just giving you a visual example. So for anyone who didn't understand it, just think that it's a billiard ball. So you are hitting it with a certain force. You're not trying to send it into the pockets. Okay. So you hit it with a certain force, so it moves in a particular direction. Okay. Now you do that again. Okay, and you keep doing that over and over again. Probably if you're doing this for hours together, by the time you reach the 10th time you hit it or 20th time you hit it, probably the force with which you're hitting it would have decreased. Okay, and you'll find that it is less affected by your attempt to hit it. Okay, probably because you're tired. Okay, so this is one example that I can give you visually to help you understand this. But basically, the shocks in the distant past will have a lesser impact compared to shocks in the more recent past. Okay? That's what this process is trying to tell you, that if you look at lags which are closer to the current value of the time series, they will have a greater impact in helping you understand why the time series is at a particular value, okay, compared to more distant lags. Just come back to this. Okay, this part you all understood. These are assumptions we are making. Okay, UT is a white noise or pure random process. Okay, these are purely the assumptions, so you don't have to understand anything about this. Okay, we are assuming that the variance of UT is equal to sigma square, covariance between UT and US, okay, or between UT and its lags is equal to 0. Okay, these are assumptions we are making. Now, if you take this part, expectation of xt minus mu t, just using this, we are able to arrive at this is equal to 0. Till here, it is clear to everyone?
Yes, ma'am, it's clear.
Okay. Then after that, okay, so because this is equal to 0, then expectation of xt is equal to mu t, okay, which is some constant. Now, variance of xt, okay, again you have to use this, okay, you're using this. So variance of xt is nothing but expectation xt minus mu t square. Okay. So once you put this in brackets and you square it, this is nothing but your summation psi j is equal to 0 to infinity. Okay. So when j is equal to 0, okay, the first term that you will get is psi 0, that is equal to 1. Okay, so you get ut. Then after that, take psi is equal to, sorry, j is equal to 1. So you get psi 1 ut minus 1. Okay. Then psi 2, j is equal to 2. So psi 2 ut minus 2 and so on. It keeps continuing up to infinity. Okay. Now once you break this up, you take expectation of ut square, that is sigma square. Similarly here it is sigma square. Now the psi's are common, right? So you take them as common. Psi j, when j is equal to 0, is equal to 1. Okay, so that's why we are able to write this. So you get sigma square is equal to summation j is equal to 0 to infinity psi j square. Okay, the psi's are some constants, so they also get squared. So this gives you the variance of xt. Is it fine so far? You'll have understood. This is
Ma'am,
purely a derivation.
ma'am, psi is the weight attached to the error term, right?
Yes.
Ma'am, so it will be constant for all the terms.
Yes.
Ma'am, why?
Those are assumptions that you are making again. Okay.
Oh,
So when I'm
okay.
telling you something is an assumption, you have to take it as given and then proceed from there. Okay. Why is that? Why are you making that assumption? If we go into that question, then we won't be able to proceed. So these are assumptions that the psi j's are constants, that ut is a white noise process. So these things are true for ut. Okay. So variance of xt is nothing but your gamma 0 or the covariance at lag 0 basically. Up to this point, is it clear to everyone?
Yes, ma'am.
Okay. The other people, I think Neil, have you understood now?
I'm catching along, but I will not lie and say that I understand it extremely well. But it's
Okay.
fine, ma'am.
Okay. You're able to understand the derivation, right? How we got.
Yes, ma'am. I'm understanding why we are. I'm understanding how we are moving. I'm just not understanding why we are moving.
Okay, fine. The answer for why are you doing all this is because when you actually go ahead and do your practicals, it shouldn't be that you're simply mechanically pushing buttons or copy pasting commands or being told, I mean, doing what exactly you're being told without understanding why you're doing it. Okay? That is the explanation. Why are we going into these derivations? Because you need to understand what exactly you're doing when you're doing the practical, or how you got an AR process, why you make certain assumptions about it, and so on. Okay. Now we'll come to this part. So just look at it, okay? Just take a look at it and then do what I had asked you to do, which is take tau is equal to 2 and then start with your j's are running from j is equal to 1 to 5. Sorry, not 1 to 5. I think it'll have to be 0 to 5. No, take 1 to 5 itself. Okay, don't take 0, take 1 to 5. Just try and write it out, see if you're able to understand it. This part is clear to everyone, right? Xt minus mu t and xt plus tau minus mu t. You're looking at the covariance between these two, between xt and its lead, which is tau periods in the future. Okay, this part is nothing but your summation psi j is equal to 0 to infinity psi j ut minus j. Okay, you're taking that whole term here. Similarly, this is the same term, except you're taking into account the fact that this is tau periods in the future. Okay, in case you haven't understood, if you want me to help you along, okay, this first term here, if you take ut where t is equal to 5, okay, I had asked you to start backwards. So this becomes u5. Okay. Then this becomes psi 1 ut minus 1. So this is 5 minus 1. So you'll get 4 here. Okay, psi 1 u4 and so on. Just proceed that way. Anyone has made some progress? Are you all able to do it?
Yes, ma'am. Can you show the slide again?
Okay. Okay, so those who are not following, I'll just repeat. You will start with 5. Okay, so this will be expectation u5. Then this is psi 1. u5 minus 1 is 4. So this will be u4. Psi 1 u4. Okay. Then since you have taken tau is equal to 2. Okay, so this will be psi 2 u5 minus tau is 2. So 5 minus 2 is 3. So psi 2 u3. Okay, and proceed in that way.
And the last term will be only psi phi, right?
Where are you talking about?
The last term in the first bracket will be only sci-fi.
Just a minute. Sci-fi. Let me check. This was 2 and 3, so then it'll become 1 and 2 and 0 and 5. Yeah, correct. Sci-fi U0. Okay.
Okay. But ma'am, what exactly is U0? Is it like, does it exist, or is it just something we're assuming it exists?
You're assuming that it exists because at time 0, generally, you can think of it as the initial value of the UTs.
All right. You asked us to suppose tau is 1, right?
2
plus 1 lag of
no 2.
2. Okay.
Tau is equal to 2 and you're starting with from t is equal to 5. So this was U5. I asked you to proceed that way. Once you do a couple, 1 or 2, you'll be able to follow because the numbers one number will keep increasing, the other will keep decreasing. It'll be like that. Have you all finished?
Just a minute.
Once you finish the second line of your derivation, right? What you need to do is just eliminate all the cross products.
And won't they add up and not cross out?
Once you take expectation, right, the cross products will vanish. For example, if you're taking ut and ut plus tau, expectation ut plus tau will be equal to 0.
Oh, yes.
So that term will vanish. Okay, similarly, ut minus 1, this term will vanish, and so on. Only where you have ut, okay, for example, if you have u5 and u5 somewhere, that term will appear in the next line of your derivation.
So ma'am, we will basically get all the sigma square out common.
Yeah.
And then you'll have expectation of psi 2, expectation of psi 3, expectation of psi 4, and expectation of psi 5.
Okay, just give me a minute. I'll show you all the answer. Okay, so you can cross check whether you got it right. Okay, so just check if your answer is correct. You're able to see this, right?
Yes, ma'am. The subscripts of the psi add up, and they're always the same.
Yeah.
I mean, the difference between the two is always the same.
Yeah, the difference between the two is always the same. So here you'll find that it's equal to 2. Okay, this was psi 0. Okay, so it's still 2. This is also equal to 2. So your lag is maintained. Or you're looking at the covariance between the same lags. Right, so just check your answer. Meanwhile, I'll quickly go through the attendance. All right. Can you all still see this? Yeah. Just give me a minute. I'll quickly just go through the attendance. Those who did not understand, just go through it. I'll explain in greater detail in the next class, okay? And you'll probably understand once we start AR processes why we are doing all this sort of derivation. All right, today we'll start with IBAF students. Uh, I'll share that particular answer with you all right? Ayush Sharma,
Present, ma'am.
Alisha Gupta, then Anam Vidhi.
Present, ma'am.
Okay. Anant Prabhat, Anant, right? Anant Prabhat, Anish.
Yes, ma'am, present.
Okay. Anant is absent, right? Anish is present.
Yes, ma'am, present.
Anjali,
Present, ma'am.
Arshada,
Present.
Barkha. Barkha is absent. Yeah. Then Bhavya, Saloni, Chaitra, Devam Pandey, Diksha, Gorja, Gayatri,
Present, ma'am.
Govind,
Present, ma'am.
then Savan.
Present,
Savan.
ma'am. Present,
How
ma'am.
do you pronounce your name? Sorry.
Savan.
Savan. Okay.
Yes, ma'am.
Then Himanshi,
Present, ma'am.
Indu.
Excuse me, ma'am.
Indu is present. Ishita,
Present, ma'am.
Kanika, Karthik Mittal, Hastro, Lakshay, okay, then Mahi, Mansi Gupta, Matangi, Megha, Nancy, Neha, Pratishtha,
Present, ma'am.
Rohan, Rohit, Samidha, Shivangi, Simran,
Present, ma'am.
then Srishti, Tanu, Tarang, Kalyani, Twinkle, Vaishnavi, Vanshika, Vibhur,
Present, ma'am.
Vidushi, Yash, Vidushi is absent, right? Yash, all right.
Excuse me, ma'am.
Yes,
Ma'am, Devam is present.
who?
Devam.
Devam. Why didn't you answer earlier?
I don't know why my mic is not working.
Just give me a minute. Remind me once I finish the other class.
Sure.
Okay. Yes, Mihir.
Yes, ma'am.
Then Akash Singh, Achal, Ayush,
Present, ma'am.
Adyasha, yeah. Tejas, Ali,
Ali
Ali
Asgar
Asgar.
present, ma'am.
Yeah. You call yourself Ali Asgar itself, right?
You can call me Ali, ma'am. It's okay. Ma'am, I'm present. You've marked me absent.
Anjali, Anmol, Arismita, Avni, Ayushi, Ramesh, sorry,
It's
Sarvesh.
Saresh, ma'am, present.
Sarvesh, sorry. It's a little confusing because
Yeah, it's okay.
Bhavya, sorry, you're present, yeah. Bhavya, Terry, Diksha, Deepansha,
Yes, ma'am.
Gaurav,
Present, ma'am.
Gaurav again, Santosh,
Present, ma'am.
Himanshi, then Jaideep,
Present, ma'am.
Ayushi, Krishan Kant Shukla, Ayushi is absent, right? Jaideep, you're present? No.
Yes, ma'am. Present, Jaideep.
Then Kriti,
Present, ma'am.
Mansi, Mansimran, Manvi,
Yes, ma'am. Manvi present.
Mihir,
Yes, ma'am.
then Muskan,
Present, ma'am. Ma'am, I was present yesterday also. Due to some emergency, I have to leave at 4:20.
I don't know what to do about that. I'll just highlight it.
Okay.
Muskan, right?
Yes, ma'am. I was present yesterday also and today also, and I'm present today also.
Namrita. Next time, if you have to leave, just type a message in the chat box before you leave. Okay?
Okay, ma'am.
Namrita. Then Neil,
Present, ma'am.
Nikhil,
Yes, ma'am.
then Prasoon
Present,
Sharma,
ma'am.
Pratik,
Present, ma'am.
sounds like you just popped in, then Rachit,
Present, ma'am.
Rahul,
Yes, ma'am.
Rahul Giri, Rahul Goswami, Rajaditya,
Yes, ma'am.
Rashi, Rishabh, Ruma,
Present, ma'am.
Rishabh is here, Sahaj,
Present, ma'am.
then Samiksha, Sharanya. Okay. Shubham Kumar.
Present, ma'am.
Which one is present? Shubham Jain.
Yes, ma'am.
Shubham. Okay. Shubham Kumar. Ram Shankar. Someshwar Ram Shankar Verma. Stuti.
Present, ma'am.
Those who have answered, you can leave if you have another class.
Ma'am,
Stuti.
I'm present.
Yeah,
Ma'am, you marked me up.
sorry, I corrected it.
No problem, ma'am.
Sanika.
Present, ma'am.
Then Vinaya. All right. So we'll meet in the next class. Just try and work out that derivation, okay? And go through it once, see if you can understand. We'll discuss more about it in the next class. All right. Thank you.
Ma'am, just a few requests.
Yes.
Ma'am, if you could please share these notes which you are presenting in the class, it will make it really easy for us. Not only if you could, if you could share the notes before the class, so that way we could be we will also be able to at least see what we're gonna do today.
Yes, ma'am, it would be easier for us.
Okay, I will try my best, but I can't guarantee that you will get it before the class. Okay, but
So even after
definitely,
will work that way, no?
yeah, after will be easier for me. But yeah, I'll try my best.
Yeah, and any
right.
reference books for this, ma'am, because we've covered 4 classes till now, so it's better to start studying before annually.
Is the syllabus available to you all?
The one on the website is from 2018, so I'm not sure if that has changed till now or not.
I think it's the same one, if I'm not mistaken. I think they are trying to prepare a revised one, but you can use, in terms of the reference books, I don't think there'll be much of a change. So you can use the same books which are listed there. For example, for the first portion which was covered yesterday, you can use Campbell, Low, McKinley. Then you can use Rousset. I think even Chris Brooks has some of the content. Basically, those portions will be the same, whichever book you refer to. Okay, maybe the notation might be slightly different. So that you can refer to any book. This wall decomposition and all these things are there even in Rousset. The notation might be slightly different, but you'll be able to follow it from there also.
Okay, and now one last thing.
Yes.
So it's actually a request. Many of the professors are now using a writing pad or something, so it makes it really easy to understand. So if you have that facility available, or if the institute can provide you with one, because it gets really difficult to study statistics and econometrics just by seeing something.
Yeah, I know that, but I don't have
It's a
one.
request.
And
Yeah, exactly, ma'am. So it's a request. If if you could request the institute to provide one or something.
I doubt if that's going to happen, and it's probably better that I don't request for something like that, since I'm just a guest faculty. Okay? So I'm not a permanent employee of the institute, so I don't think I can make such a request. So we'll try our best. Let's see if I can figure out some other way to maybe write the equations during the class itself.
Okay, sure, ma'am. Thank you so much.
Okay. All right, so we'll meet in the next class, and I will try and share a data set also for next week's practicals. Probably Friday we'll cover some theory, and then Saturday we can do some practicals. Right, so we'll meet in the next class. Thank you.
Ma'am, please mark my attendance.
Thank you, ma'am.
Yeah. Just a minute. You're in IBEF, is it?
Yes, ma'am. Yes, ma'am.
The rest of you can leave. Just tell me your name again.
Devam Pandey.
Yes. Okay. Done.
Thank you, ma'am.
Ma'am, Anmol as well.
Yeah.
Anmol.
Anmol for which? The previous week? I mean, last class.
Today's class.
When? Why haven't you answered your attendance?
I guess there was some network issue, but I was present in the class.
See, if you don't answer at the time, then it's going to be very difficult. I will be marking you absent, okay, if you don't answer at the time itself. Or
No,
even
ma'am, I was present in today's class. I guess there was a network issue. You can check, like, I was present in the entire class.
all right, from the next class onwards, if you're not telling me right after I've completed attendance, then I will not be able to give you attendance. All right?
Fine, thank you.
You're in FE?
Yeah.
Okay.
Thank
Could
you.
you share the recording if possible?
I think it's being shared in this group itself. In the mail ID. It's not available to you all, is it?
I haven't got so far anything. So
Okay, fine.
you
Fine,
just
I'll...
tell the admin guy, he will take
Okay.
care of it.
Okay, fine.
Thank you.